Going to tell us about understanding the invariance of visual features with separable subnetworks.
All right, is this on? Cool. I'm really tall. Hi, everyone. Thanks for coming to my talk. This is work I conducted under the tutelage of my advisors, George Alvarez and Talia Conkle. Okay, let's get right into it. What's a visual feature detector? Broadly, it's just a function that takes in images and outputs scalars. So we're familiar with like simple feature detectors, right? Maybe they take in an image of an edge, and maybe this feature detector doesn't really care about this orientation, but as you rotate the edge, the feature responds in a systematic way. We often even have the analytical functional form for feature detectors like this. Okay, so this work is concerned with what I'll call a complex feature detector in contrast, which has a big receptive field and takes in natural images. And these are usually harder to understand, right? They're ostensibly detecting something, but the function is pretty complicated and it's not always obvious what that something is. So one avenue into understanding a complex feature detector is to think about its invariances. So for neural features, which have sparse responses and are thresholded at the bottom, we can think of invariances as just the images and image manipulations that yield a high response for that feature, right? And some of these invariances are really pragmatically motivated, right? So like if we have a chair detector, we'd expect it to be scale invariant. It should be rotationally invariant. It really should be invariant to any affine transformation in pixel space. And maybe pragmatically similar, but computationally different, you'd want the chair detector to be viewpoint invariant. You know, empirically in neural systems, you can find this other kind of invariance, right? Which I'll call heterogeneous invariance. So maybe you have a feature and it likes faces, but you observe that it also likes bowling balls and it also likes basketballs. So this is also invariance. Maybe we can understand it in the same way. Okay, so how are feature invariances generated? Here we're going to consider two possibilities. The first I'm going to call subfeature disjunction. Here the idea is you have subfunctions that detect one part of the invariant structure. So maybe a chair detector is really the combination of a front-facing chair detector and a back-facing chair detector. And the invariant detector adds those together. Maybe the ball face detector is just a face detector added with a ball detector. Now this is in contrast to what I'll call a latent feature detector, where there's just a latent commonality across the images in the invariant structure. So remember, the invariant chair detector is really just a spokey box detector, right? And the face ball detector is really like an orangish circle detector, and you don't need distinct subfunctions. Okay, so how does this work? This distinction pan out in artificial neural networks. So here a feature is just going to be an artificial neuron, right? And we can think about disjunctive feature detection first. So in this case, maybe the face image gets passed in and it takes a certain route. These are the computations responsible for why the feature responds highly to the face. Now, this is in contrast, if it's a disjunctive feature, the bowling ball would take a different route. There are different computations responsible for why the feature responds highly to a bowling ball. Okay, latent feature detection, this is the route. And for the bowling ball, the route would be the same. It's the same computations detecting the latent common feature between the two images. Okay, but really in this neural context, right, it opens a whole continuum, right? Like maybe the ball uses the purple computations and these blue computations, and the face uses the purple computations and these orange computations. So we can quantify this continuum, right? Just as the intersection over union of these subnetworks. A totally disjunctive feature would have 0 intersection over union, and a totally latent feature would have the intersection over union of 1. And then some amount of overlap would just be something in between 0 and 1. Cool, but you might be like wanting to stop me and saying, wait a second, neural networks don't route images. It's just this monolithic feed forward function. You press go and everything gets computed. So what's going on here? If we've spoken before, maybe at VVSS last year, you'll know that my answer to this is that visual neural networks really route images implicitly. So let's define what I mean by this. Okay, we have a latent or just a feature in our network. We're going to say we have a subnetwork for that feature. If we can delete the whole model and just consider the computations in the subnetwork, and the feature is unaffected, it responds to images the same as before in the full network. Now, how do we find these subnetworks and do they exist, right? This is a combinatorially explosive search problem. So what we've done is developed an algorithm that I can't really get into here, which I'll call a subnetwork pruner. And what it does is take in a model and a feature, it takes in an image set, and it takes in a sparsity level, how many edges you're allowed to preserve in the subnetwork. And what it's going to output is a subnetwork at that sparsity level that preserves the features responses to that image set. Cool. Okay, so we're going to use this algorithm to explore three features, right? Latent, I shouldn't say latent because that's ambiguous now. Three features in AlexNet trained on ImageNet. And we're going to see if each of those features is a disjunctive feature or a latent feature. Okay, so how do we find interesting features for this analysis? One way is to look at a feature's top activating image patches from ImageNet. And when you do that, sometimes you'll identify what have been called these polysemantic features. So this feature seems to like terriers and it likes metal lines. Okay, so it seems like a good candidate feature for disjunctive, right? Maybe it's the combination of a terrier detector and a metal lines detector. Now, this is an empirical question though, right? Like it could be that there's a latent commonality between the two that we just can't perceive. So we're going to arbitrate on this distinction by extracting subnetworks. We'll extract a subnetwork that preserves the features responses to terriers and a different subnetwork that preserves the features responses to metal lines represented here in orange and blue. We can do this at different sparsities. So that's on the x-axis here. And on the y-axis, we have a normalized metric of feature degradation. So minus 0.2 means the subnetwork feature is responding on average 20% less to its target data set than the original feature in the full model. So you can see like we can meet our targets pretty well and we can get pretty sparse. But the pivotal question here is, right? If I extract a subnetwork for terriers, how does it respond to metal lines? Okay, that's shown here in the dotted lines. So if I extract a terrier subnetwork, its responses to metal lines is going to degrade much quicker than its responses to terriers. And what about our intersection over union metric? To get that, we can just set a threshold of tolerance for feature degradation and look at some particular subnetworks at that sparsity that meet that threshold. When you do that, you can look at the intersection over union. You can do that layer-wise, right? So here we see really early on, these two subnetworks are the same. They use the same like Gabors in low-level computations. But as you go deeper into the network, they totally separate. We're also seeing here feature visualizations for each subnetwork. And we can see that those separate out as well. We've really isolated the terrier subnetwork and the metal line subnetwork in this neural network for this feature. Okay, and just as a sanity check, what happens if we mix the image sets? This doesn't hold, right? The image set 1 subnetworks work just as well as ImageNet 2 or image set 2 subnetworks. You don't get the same pattern. And we can look at 2 particular subnetworks at a sparsity, and you'll see that they totally overlap. It's the same subnetwork. So you have to find the right cleave in the data. You can't just pick some arbitrary data set and find a subnetwork that's going to preserve uniquely to that image set. Okay, and we can do this with other polysemantic features as well. So here's a monkey and text feature detector that's polysemantic, and we see the same pattern. We can separate the subnetworks. We can look at their intersection over union, and these are even less overlapping, and the feature visualizations separate out really nicely. Okay, cool. So these polysemantic features seem to be disjunctive. Okay, next experiment. Here's a feature that seems to respond to these like concentric circles. So same thing. Maybe this is this disjunctive combination of a big circle detector and a small circle detector. Or maybe there's like, it really needs to be concentric circles, or there's just some general circle-ishness latent feature that this feature is responding to. So we're just going to play the same exact game as before. You can make a little prediction in your head about what you think it might be. It's the same. It's disjunctive. If you extract a big circle subnetwork, it's not a good small circle detector, and vice versa. We can look at the intersection over union at a particular sparsity level that passes our threshold. And we'll see that they totally don't overlap here, going back even farther, even into the first layer. And the feature visualizations separate out nicely. We found a big circle detector and a separate small circle detector. Cool. Okay, so this is even more disjunctive. Okay, in the final experiment, we're gonna analyze this seemingly face detector from its top activating image patches. Now, its top activating image patches are all front facing, but this feature also likes faces and profiles. So we can ask the question, is it the combination of a front face detector plus a profile face detector? Or is there just some face ishness common to faces in front, on, and profile views that this feature is a detector for. Okay, so to do this, I just made a little data set of images from Pinterest because I could identity match. They have all these like pictures of people like this. And so we have 60 images per category and they're identity matched. And make your prediction. What do you think is going to happen? It's not the same as before. If you extract a front face subnetwork, it really works just as well as a profile face network. Okay, and at a particular sparsity level that passes our threshold, high intersection over union, they're the same subnetwork and the feature visualizations don't separate. Cool, so it's latent. Okay, so in conclusion, I just want to head off a certain interpretation of this work, that vision combines monkey faces and text into a single representation, or that it utilizes separate computations for shapes at different scales, or that vision processes frontal and profile views the same. That's not quite the point. This is just particular features in ImageNet trained AlexNet. I don't know if you want to generalize from these features. What people are doing is coming up with neural network encoding models for biological visual features. And I hope a lot of you are doing this sort of work. I think that's really important work. What we're trying to do is develop tools for interpreting neural models. So if you have a model on the left here of a biological feature that you think is interesting and a good model, and you want to understand how that feature works, well, we've got a bunch of tools basically to dissect that feature into its component parts and really look at the data processing necessary to get that feature. So in conclusion, I'd like to thank the Harvard Vision Sciences Lab, and you can check out the code and do this yourself at this GitHub link. Thank you.
It's a really cool talk, thanks. So have you looked at the responses to images that aren't maximally activated to your preferred subnetwork, and how do they change when you delete subnetworks?
Yeah, let's see if I can show you a good example. So for example, looking at that face, that looking at that, for example, circle detector, you can do the same thing for like the images it doesn't like, right? So this doesn't like squares, but at two particular orientations. And you can actually do the same thing. You can extract like the relevant sub-inhibitory networks, for example. So here we've extracted the subnetworks that inhibit at the two individual orientations. And then you see the activation. This is like in 2 dimensions over rotation and size that just isolate the inhibition at one orientation or the inhibition at another orientation. And the feature visualizations are negative feature visualizations, images that that subnetwork really doesn't like. So you can do a bunch of stuff with this. I wasn't speaking to the mic. I hope people could hear me.
Hey, I was wondering, when you were looking for all these like disjunctive features that kind of you can perceive one or the other to test on, like how did you select them? Did you kind of just
so this
through
is
them?
also much more complicated than I let on.
Yeah, 'cause it seems interesting if you can just
In
find a lot of
actuality,
these.
yeah, what we did was like do some like clustering at the population level. So you can think of a good candidate disjunctive feature as one where even though it responds highly to both sets, at the population level, they're encoded super differently. So we look at the population response in the layer, and if those population responses were clusterable, those were actually those were how we selected those. We didn't just do it by eye. So you can be clever there too. Yeah.
Hi, so nice talk. This approach kind of assumes that you can interpret in English every unit in the network, and I want to know if you have some reason to believe that's well-founded.
So
and if it's not.
This work is inspired largely by this work. You should really check out that's really cool by Chris Olah and company, which he calls like circuits. It's on this publication called Distill Online.
The circuit part I like, but the requirement that you have a label.
Yeah, I mean, maybe you don't have a requirement that you have a label, right? So like, for example, at the very end here, we look at some, if you look at this tool, we're kind of like visualizing at the top here, we're visualizing like this particular kind of feature that maybe doesn't have an obvious label, but nonetheless, we can try to understand by this the subnetwork is sparse enough to just look at all the computations relevant leading to that feature. So you don't
But I'm
necessarily
not-
need a
You know, I
semantic
guess
label.
I'm not sure what that tells us.
It